This is a video to help you understand analogWrite. AnalogWrite's a function both in the Arduino framework and the AVR framework. And there are two issues with the analogWrite function, which is one, it's somewhat misnamed. It doesn't really do an analog write. And two, it deals with this concept known as PWM, or pulse width modulation. And so let's talk about pulse width modulation so you can understand that concept, and then just use analogWrite to change the PWM on particular pins. So on your screen, or on my screen, you can see that I've got three windows. One window is my code editor, where I'm looking at the Blink program. In the upper right-hand corner, I have my terminal program, where I will just execute make flash, and then you can see I've got a camera focused on an Arduino Uno with both regular yellow LED plugged in and then an RGB LED plugged in. And so we'll go through those two in a moment. So in the Blink program, let me type this in as high, save that, run this, and you'll see now it blinks and it's pretty bright. And it's just a blinking program that we've all learned to know and love. Now let's go back to Blink and let's change it to 5 milliseconds instead of 500. So instead of blinking at half a second, it blinks every 1/1000th of a second. Let's save that and let's do make flash. And we'll watch it blink. And it's not blinking. Well, it is blinking. We just can't see it. And to confirm that it's blinking, let me show you what this looks like on an oscilloscope. So an oscilloscope shows the waveform at any point in time. What we mean by that is it shows the voltage across the LED over time. And what we're seeing is that the voltage is actually high. Here's 5 volts right here, the 5. And then here's 0 volts here. And so it's high for 5 milliseconds. It's low for 5 milliseconds. High for 5, low for 5. And the point of this is that when you get to something like this, and so these things over here tell us the period. The period is the total time it takes to go through one complete wave. One complete wave. And so that's 10 milliseconds. And then 1 over the period is our frequency, which is 99.7 hertz. It's actually 100 hertz, meaning it happens every 100th of a second, or it happens 100 times a second. And then our duty cycle, which is the amount of time that it's high, is 50%. And you can see that visually, that it's high for 5 milliseconds, it's low for 5 milliseconds, high. And so 5 over 10 is 50%. However, when we go back to our LED, we see that it is apparently on all the time. And the reason is that the human eye can only discern down to about 60 hertz, or up to about 60 hertz. And anything over 60 hertz, or 60 times a second, the human eye just perceives that to being on all the time. And you see this happen on televisions and things like that, where the scan rate used to be at such a high rate that you just would only you'd see these moving pictures, and your human and the eye would deceive you into thinking that it was one consistent image. So that's this concept of, and then if we go back to the oscilloscope one more time, these vertical bars are called pulses, and then there's a negative pulse here and a positive pulse, negative pulse. So that's this thing is the pulse. The width of it is how wide it is. And then as it changes, it's modulated. And we'll get into that in greater detail. And so in this case, we're just dealing with a pulse width of 5 milliseconds and a period of 10 milliseconds. So let's go back and change this Blink program in such a way that we're now on for 1 millisecond and off for 4 milliseconds. And what happens then? And so when we do that, we say make flash, it's on, it's a little dimmer than what it was before, but it's readily noticeable. And what's fascinating about this is now you can see that the pulse width is dramatically different. And if we go, don't need to do that, we'll reset it. And we see that it's 5 milliseconds, but we now have what's known as a duty cycle of 20%. Now, why is that important? Well, think about if the pulse is always on, that's a duty cycle of 100%. If it's half on, half off, it's a duty cycle of 50%. And if it's only on for 20%, it's a duty cycle of 20%. 20. Let's convert that to dollars. Let's say it costs $10 a month, $10 a month for the energy required to drive that LED at 100%. Well, we could save $5 if we only had it on 50% of the time. So now we're only at $5 a month. And now if we're doing a duty cycle of 20%, it's only costing us $2 a month to power that LED as compared to $10. So there's some significant savings you can get by pulsing an LED that continues to look like it's on, when in reality we know it's only on for this period of time. So that's what's called as changing the width of the pulse in order to decrease the duty cycle and then decrease the amount of energy required. So that's great for dimming an LED. In fact, you can even tell the LED is a little bit dimmer. However, when we go to our blink example, we don't have a lot of leeway here. We only have 1 and 4, and we could go to 1 and 1, or there's just not a lot of space there. So there's another way of doing this, and that is what's called, and I'll go ahead and just type it out. I'll go ahead and comment this out, and I'll introduce a new command, and it's analogWrite. So there's analogWrite, and we'll use the LED pin, and we'll say, in this case, we're going to give it a 50% duty cycle, and I'll explain why the 127 in a second and not 50. And we're going to have to include analogWrite right here. Okay, what analogWrite looks for is a number between 0 and 255 for the second number. The first number is the pin. The second number is the duty cycle expressed as a number over 255. So it's a value over 255. So 127 is approximately half, or is half of 255. So this means it's going to be a duty cycle. So now what we do is we say save. Now we have a 1 command blink program. We say make flash, and looks virtually the same. Except now I have a lot more leeway. I could actually even take this down to, let's say, 31 and compile that. It looks a little dimmer, and then let's take a look at the oscilloscope, and now we can tell, and we'll reset this, and it says it's 12.5% duty cycle. And I can see on my in looking at the LED, it's noticeably dimmer. However, we're able to see it, we're able to use it, and it's only using 1/8 of the energy that would be required at 100%. Okay, so that's great. That's one way of looking at it, and we can see just instantly why power savings would work for an LED. Let's think of another way of doing it, and that's if we had an LED that used 3 LEDs, and that's what's known as an RGB LED. An RGB LED, which is this little physical device right down here, it has a red, green, and blue LED, and we can see that. Why don't I just go ahead and show that? So if I say, right now I'm writing to the blue pin, so if I say make flash, it'll now show up blue. And let me just adjust the exposure a little bit. Oops, I think, well, you can see it, a very strong blue tint. There we go. We'll go with that. And so you see a blue tint, and let's replace this. Let's make that 0 and make this 127. So we now are writing the green one, and we say make flash. And now we have a green tint. And it actually, if I look at the LED with the naked eye, I can see that the LED is clearly green. And then if you do the same thing here and make this one 0, save it, then you'll have, yes, a red tint. And so we have a single LED that can be red, green, and blue. Now, if we have that, then what we can also do is say, well, what if we said 127 on red and green? What do we get? Well, red and green are, it's yellow, and it's very definitely yellow. It just kind of blows out the camera right now, but it's a definite yellow LED. And so by just a simple command change, we can now create different colors. And so if you did, for instance, red, if you do a combination, and we'll also take it down a little, I think it's like 31, and let's just do about 8 here, and then do 16 here, and we save that, then we get, it's a lovely, in this case you can't see it as well, but it's a lovely kind of light purple color. And so very easily we're able to create colors of an LED by just changing these 3 commands. And what we're doing is that we are changing the width, the amount of energy that's delivered to each one of those LEDs, and then the human eye is taking those 3 LEDs, combining them into a color, and seeing it from a combined color perspective. I don't see a little bit of green, a little bit of blue, a little bit of red. I see a combination of those 3, which is like a light lavender. Now, to finish with this, so this is great from an LED perspective. You can see how we can save energy, or we can create different colors. But then the last one, think about this from an electric vehicle perspective. You can use PWM from a motor perspective, and you can take out the LED and put in a motor and change the PWM. You change the width of the pulse, is going to change the speed of the motor. And so you can see how you can accelerate and deaccelerate by changing the speed of the motor with PWM. And then also the benefit of that is it changes the amount of energy required by the electric motor. So instead of raising the voltage level to increase the speed of the electric motor, you change the width of the pulse. It decreases the wear and tear on the battery, which means your battery lasts longer. It provides longer current over time, and you have electric vehicles. And so that's the concept of PWM. AnalogWrite as a function, the only thing it does is it takes a pen and it takes the duty cycle, and then you use that duty cycle to drive things somewhat in an analog way. But the best way to understand it is you're changing the width of a particular pulse.